memorize the pKa tables. Okay. We got charges, all that stuff is done. Good. All right. Okay, so flip back to this. I'm going to do this problem right here. This is an example of a question where they want you to solve for the pH of a reaction between sodium aspartate and HCl. You won't be given this exact one, but the way we solve this will be very similar to how you solve the question on the exam. So what we're given here, let me write down the information on the paper, and I'll flip to here. Sodium aspartate and HCl. Okay, and they want the pH. So, all right. Okay. So, a reaction between an amino acid and a strong acid, or a strong base. It could have been a strong base also. Basically, it's the exact same procedure as the one that we did for phosphoric acid, where you have to do stoichiometry, then you do Henderson-Hasselbalch, and you get the pH of the solution, okay? This question in a word problem format would tell you that you are reacting 0.1 moles of sodium aspartate plus 0.12 moles of HCl, and they want you to figure out the pH of this solution. So, what you should start with is draw out the reaction. Sodium aspartate, whenever you see that, it's a shorthand notation for sodium with a +1 charge, and aspartate is going to be at a -1 charge, okay? Sometimes they may use other phrases such as monocationic aspartic acid. I said cationic. You go look in your general chemistry notes or physics notes or whatever. If it said instead cationic aspartic acid, what charge would that aspartic acid have? +1. Cationic, and my high school chemistry teacher taught me this. Cats have pause. So cations are positively charged, okay? So if it said cationic aspartic acid, you should write down ASP +1 and then continue with the rest of the problem. If it said dicationic arginine, you're going to write down arginine with a +2 charge, okay? And then you continue with the rest of the problem. Yes, question?
Would they say like monocationic, like, but then that means sodium, like that they're referring to sodium?
No, because because the sodium doesn't matter. They're just telling you, and they'll either draw sodium there or they'll just blatantly tell you monocationic something, and then you write down that amino acid with a +1 charge. And if they said anionic, negative charge, okay? All right, in this problem, we have sodium aspartate, which is a fancy way of saying I don't care about sodium, I care about aspartic acid with a -1 charge, okay? Plus HCl, which is a strong acid. In this reaction, HCl is acidic, and ASP -1 charge is going to act as a base. We know with acid-base chemistry that this hydrogen is going to be given to the aspartic acid. So we are going to make ASP with a 0 charge plus some chlorine, which doesn't matter. Does everyone follow? When you are doing acid-base chemistry, the thing receiving the hydrogen is going to become more positively charged, right? Because hydrogens are positively charged. The thing giving away the hydrogen is going to be negatively charged, right? So in our example here, in this acid-base reaction, HCl is going to give a hydrogen to aspartic acid -1, and it'll change the charge on that aspartic acid to a charge of 0, okay? This is our reaction. We are treating this the same reaction as like with phosphoric acid. We're trying to solve for pH. Yes?
Would we still have 0.02 moles of the hydrochloric acid?
We're going to get to that in a bit, yeah. So, you write out this and you write out the components of this reaction. You do the same thing with phosphoric acid. You do stoichiometry. Remember, first step in stoichiometry, figure out the limiting reactant. That's this thing right here. So we do some stoichiometry. Minus 0.1, minus 0.1. We started with none of the ASP0, and we are producing 0.1 of it. So, some stoichiometry, we end up like this. We end up having, after one reaction, 0.02 moles of HCl left over and 0.1 moles of ASP0 left over. Am I allowed to use Henderson-Hasselbeck right now? No, because we still have HCl left over. I must continue with this reaction. So, ASP0 plus HCl. If we're adding another hydrogen, ASP0 now becomes ASP plus 1 plus chlorine. That chlorine doesn't matter. Let's fill in the numbers. We ended up having 0.1 moles of ASP0, and we ended up having 0.02 moles of HCl. Stoichiometry, HCl is our limiting reactant because we have less of it. We subtract that amount. And we add that amount to our reactants. Now am I allowed to use Henderson-Hasselbeck? Yes, because we have run out of HCl. Okay? We only have our weak acid and our conjugate base here. And we're going to answer in a second which one is the weak acid and which one is the conjugate base in a second. So the bottom line of this equation is we're trying to solve for pH of this reaction. So Henderson-Hasselbeck says pH equals pKa plus log of the conjugate base over the weak acid. All right? Well, we are given these amounts here. We have to figure out which one is our conjugate base and which is our weak acid. I gave you a shortcut earlier. The shortcut was whichever one is more positively charged, has more hydrogens in it, that one's going to be your weak acid. Okay? It doesn't matter if it's a product or reactant. The one that is more positively charged, you are going to use that number as your weak acid number. So, and the one that's less positively charged or more negatively charged is going to be your basic one. So, plus log of 0.08 over 0.02, right? Because 0.08 represents aspartic acid 0, and 0.02 represents aspartic acid with a +1 charge. In order to solve this, we need to figure out the pKa to put here. And I did not start with this, but I should have. I can figure out the pKa by drawing out the charge diagram for aspartic acid. I won't go into details. Once you learn how to draw a charge diagram, you will know that for aspartic acid, you can draw the charge diagram like so. And that's because it's acidic, that's because it has 3 pKa's. It's going to look like this, okay? You fill in the pKa's in the table that would be given to you. It's something like this. I might be slightly off. You'll have to go look at the side chain pKa for aspartic acid. I don't know it off the top of my head. It'll be given to you in a table. This is your charge diagram for aspartic acid. Okay. Which one do I use? Well, what was our last reaction between aspartic acid 0 and aspartic acid +1? Let's see. According to our table here, I should use a pKa of 2, right? Because we are jumping from aspartic acid 0 to aspartic acid +1 charge. We are crossing over this pKa of 2. That goes right there, okay? And now, I'm not going to plug it into a calculator. You have everything to solve for pH of this question, okay? Again, this question is asking, given sodium aspartate and some HCl, figure out the pH. You treat it the same exact way as you did for that phosphoric acid question that we did. We do stoichiometry until we run out of our strong acid or our strong base. Then we plug in the corresponding numbers. You choose your pKa based off the charge diagram when it comes to an amino acid. And that's because, and we know that it's a 2, that the pKa is 2 that we should use, because our last reaction was between aspartic acid 0 charge and aspartic acid +1 charge, as drawn right here. Okay? Yes. Yes, we had to do two reactions here. So we aspartic acid. If you, I don't know if you came in after that, but for amino acids, some of them have 3 pKs, some of them have 2 pKs. You can watch the recording when we were talking about that part. Okay. All right, we're good. Let's see. Let me go back to my list here. Okay. You should know, and this might have been talked about briefly, I did see it in the PowerPoint. In biochemistry, we use terms like L configuration and D configuration to describe chirality. It's not R's or S's like in organic chemistry. In biochemistry, we use L configuration and D configuration. Don't worry about having to identify which one is which given a picture. All you have to know is that amino acids, naturally occurring amino acids, and maybe one of you know this, is which one of those? L configuration. Naturally occurring amino acids are L configuration. You don't have to know what that looks like, you just need to know that they're L configuration. And one more question regarding configuration. All right, one more question regarding configuration. Which of these carbons tells you whether the amino acid is L or D configuration? It is the alpha carbon. It is the central carbon that you draw in every single amino acid when you're memorizing amino acid structures. The carbon that tells you whether you have L configuration or D configuration is this central carbon. You will not be asked, if given a picture, if it's L or D configuration. You just need to know ahead of time that naturally occurring amino acids are L configuration, and it's this carbon that will tell you that. Okay, the alpha carbon. Yes.
What about D?
D configuration, I believe, is actually just you flip these two things around, but that doesn't occur in nature. You don't have to worry about that. Okay. There are, when we get to sugars, you will learn that sugars prefer the D configuration instead of the L configuration. All right. One more thing in terms of chirality. Do you guys remember that a chiral center is identified when you look at a carbon and it's attached to 4 different things, right? That's the oversimplification, but that's the quickest way to find a chiral center in a structure, is you look at a carbon and you see if it's attached to 4 different things. It turns out some of your amino acids have 2 chiral centers. One is the alpha carbon. Every amino acid has the alpha carbon as a chiral center. Some of them have a second chiral center somewhere in here, okay? One big example, I believe, is threonine. I'm not going to draw it. So you go draw it out and you confirm for me later that threonine has a second chiral center. And again, to identify chiral centers is that it's a carbon attached to 4 different things, okay? There might be more than that. I don't know. I don't remember the entire structures of all of them anymore. I don't have to. I'm not taking the class. You guys go study your structures, and given multiple choice answers, one of them may have more than 1 chiral center. The only one I remember off the top of my head is threonine, but there might be more than that. Okay. All right. All right. That is all of that, and that. Unfortunately, it was probably a mix of Chapter 4 and Chapter 5 stuff. My bad. I'm going to do now the rest of the Chapter 5 stuff. Okay.
What was the original problem
For which one?
for the one that we used to have?
This one right here. This one was found in Chapter 4 worksheets, and I believe it's the very last pH calculation question here. It's part C right here, 4 part C. Okay. So, a couple more topics. Okay, good. All right. So, Chapter 5 stuff. This was the chapter that taught you how to sequence an how to sequence a given amino acid.